Now we're moving on to question number 17. And from here it reads, solve the differential equation y prime plus xy equal to xy raised to the power 2. Alright, so we're going to solve the differential equation dy dx, it's our y prime here, plus xy equal to xy raised to the power 2. A clear observation of this differential equation tells us that it is a Bernoulli's equation, because this is non-linear first order ordinary differential equation. Non-linear because this y here is not raised to the power 1. No, for linear differential equation, y and its derivative is expected to be raised to the power 1. So here it is not raised to the power 1. And so it makes this a non-linear. Then this is specifically Bernoulli's equation. Non-linear Bernoulli's equation. Because once again it follows the Bernoulli standard. If you look at the equation, it is of the form y prime plus p of x times y equal to q of x times y raised to the power n, where our y raised to the power n is this term, n is 2. Are you following, right? This part is your p of x times y, and here your q of x times y raised to the power n. So this is how I got to know that it is Bernoulli's equation. For detailed understanding of this fact, always remember you can join the GMAT 41's classes. Is that okay? Join a full range of learning classes, and then you would get the full details about this. Remember, it's past question we are treating, and we have to be fast in doing that. So the equation is dy dx and then plus xy equal to xy raised to the power 2. Now from here, take note please, n is equal to 2, which is the power of y here, and then p of x is equal to this p of x, the multiplier of y here, is equal to x, and then q of x is equal to the multiplier of this y raised to the power 2 here, which of course is x. Now there are two ways we can solve the Bernoulli's equation. We can use the transformation method, where we use u equal to y raised to the power 1 minus n to solve the problem. All we just have to do is to differentiate that transformation in order to get the y dx, for which we would substitute for it in this Bernoulli's equation. Now this transformation method reduces a Bernoulli's equation to linear first order differential equation in terms of u and x. And then we can then solve using integrating factor method. But I'm not going to do that because I feel that is going to take me much time. I will use the formula method directly. Is that okay? And the formula method reduces Bernoulli's equation to separable variable equation, of course, faster for us to solve. Now the formula method, the formula is giving us integral u raised to the power minus n. We're going to integrate this with respect to u. And then we make it equal to integral q of x. We shall multiply this by y subscript 1 raised to the power n minus 1. This part is to be integrated with respect to x. Now I'm going to try the value of n here, where n is equal to 2. Look at it, the power of y in this q of x, y raised to the power n power 2. Then of course our y subscript 1, how do we get it? Y subscript 1 is obtained from taking exponential negative integral of p dx. Simply take exponential negative integral of this term, this x, because this is our p of x, integrate with respect to x. Is that okay? Then you are seeing here, u is equal to y divided by y subscript 1. So we know all these terms for us to use in solving this problem. The first thing I'm going to do is to obtain the value of my y subscript 1. Let us get y subscript 1 here. Y sub 1 is equal to exponential negative integral p dx. And our p of x here is this value. Look at it, the multiplier of this y, and it is x. So this is going to be x dx. Let us integrate that x with respect to x and c. Of course, we're going to get x raised to the power 2 divided by 2. So y subscript 1 is actually exponential negative x squared over what? 2. Correct. Once we've obtained our y subscript 1, we can now use this formula, okay? So let us substitute. You know, one does not need to really write out all these things when solving problems, say if it is objective case. Because of course you have all those information in your brain already, you can just move on straight. Substituting into the equation, we have integral u raised to the power minus n, which is minus 2. At this point, I don't need to fix y over y1 so that it will not be stressful for me to handle. Just work with u directly. Once you do the integration, you can now substitute for it. Then that will now be equal to, this part is integral q of x. And what is our q of x? The multiplier of y raised to the power what? 2. And of course, it is x here. We're going to multiply this by y subscript 1 raised to the power n minus 1. And y subscript 1, we have the value there, exponential minus x squared over 2. We shall integrate this with respect to x. So we've done the substitution into the formula. It is now time for us to integrate. This is u raised to the power minus 2. If you integrate u raised to the power minus 2, it's simply for you to add 1 to the power, then divide by the new power that is going to result. U raised to the power minus 2 being integrated will give you u raised to the power minus 2 plus 1 over minus 2 plus 1, which of course is u to the power of minus 1 all over minus 1. And that of course will simply give us negative 1 over u if you work it out using indices law, negative index law, okay? I've done the analysis so you can just replay and listen to the explanation. So we move on to integrating this part. How do we integrate this side of the equation? Normally, if someone looks at this and having the knowledge of technique of integration, one can start suspecting, okay, we're going to use integration by parts there. But of course, this does not require integration by parts. Why? When you use integration by parts, is simply you're given two terms being multiplied and you're asked to integrate. You now find out that if you differentiate this, you can't get this. And if you differentiate this, it cannot produce this. That is to say, derivative of any one of those two terms cannot give you the other one. Then you use integration by what? Parts. But from what I'm seeing here, it's true if I differentiate x, I can't get exponential negative x over 2. But if I differentiate exponential negative x squared over 2, it will produce an x term for me. Are you following, right? If I differentiate it, derivative of that exponential would give us exponential negative x squared over 2, would give us, differentiate the minor function, which is going to be negative 2x over 2. That's if you differentiate this term. And then you're going to multiply by, differentiate the major function exponential minus x squared over 2. That's what we're going to get. You see? This and this will cancel. So you observe that this is negative x times exponential minus x squared over 2. That is if you differentiate this term. Did you observe that it produced an x term for us? Take note. Look at this. The result gave us x, which is what you have there. So of course, we can solve this thing using the technique called U substitution. I've just explained why you shouldn't be thinking of integration by part here. So let us proceed straight on. I'm going to do this integration using U substitution, and then what do I do? Straightforward, keep this x constant. Since you know that if you differentiate this guy, it will produce this x term. So keep this x term constant, then integrate only this exponential term. That exponential minus x squared over 2, integrate it. Because we found out that if you differentiate that term, it will produce x term. So all you have to do is go to that term alone and then integrate it. Integral of this, what will it give to us? We're going to integrate the major function, which is exponential, to still give us exponential x squared divided by 2. And then all over, remember, integration, you integrate major function divided by differentiate minor function. So this time around, I'm going to differentiate this term, minus x squared over 2, which of course, if you differentiate that minus x squared over 2, is going to give you minus 2x divided by what? 2. I've done the integration. Are you following, right? Remember, in every integration, you have a derivative term there. Join our full range of learning classes, please. I'm appealing to you, all right? With a paid subscription, you can get a detailed understanding of this, and the subscription is very affordable. Look at the comment section for details. Is that okay? Now let us proceed. Having integrated this, I'll simply put plus c. But let me hold on. Here, the constant of integration in the option is a. So I'm going to put plus a. And then you would see that this 2 will cancel this 2. This x will also cancel this x. So automatically what we have here is simply minus exponential minus x squared over 2. We can now solve. This is negative 1 all over. In place of u, I've told you the value of u already. U is y divided by y1. And y subscript 1, this is the value, exponential minus x squared over 2. So exponential minus x squared divided by what? 2. That is our y1. Okay. And then that is going to be equal to negative exponential negative x squared over 2 plus the constant of integration a. Mathematically, watch something because I'm going to do it at once. I want to remove this negative from here by multiplying through by negative. Of course, that will change this guy to plus. This negative is to change it to plus. This supposedly should become minus a. But because the constant of integration, it will still remain plus a. Then again, watch. 1 over y over exponential minus x squared over 2 all over 2. Are you following, right? Exponential minus x squared over 2, please. I have to be careful of the way I write this. The over 2 is only affecting the negative x squared. Okay? Mathematically, that exponential term will go up. Are you following, right? Division of fraction, that's just simple arithmetics. So this eventually becomes exponential minus x raised to the power 2 divided by 2, then over y equal to, good. Coming here, this will simply be left with exponential negative x squared over 2, then plus a. Good, you notice that the negative have disappeared. This is my answer. But if I look at the options given to me, I didn't have that answer directly. But looking at the option, I can transform my answer here to the option. You observe that the y part alone had been made subject of the formula. In option A, option C, and D, we have 1 over y. Then option B, we simply had y equal to something. So this is what I'm going to do. Since y is a denominator here, I'm going to write this in such a way that y will be a denominator. And then here I have 1 over y. And to achieve that here, this exponential minus x squared over 2 will have to go off from here. So all I have to do is to divide this equation through, this solution through, by exponential minus x squared over 2. If you divide this term, this numerator, by exponential minus x squared over 2, it will cancel itself and 1 will be left. So this becomes 1 over y equal to, come to this term divided by exponential minus x squared over 2. It is the same term that you have here, exponential minus x squared over 2. So if it divides itself, you'll be left with 1 plus, come to this, divided by exponential minus x squared over 2. Let me just show it. All over exponential minus x squared divided by 2. And I guess we are done. I can rewrite this in a form 1 over y, and then that's going to be equal to 1 plus. If this negative exponential, that is exponential negative, if this exponential negative x squared over 2 is to go up to meet a, that negative will change to what? Positive. And so it's going to become a exponential x squared divided by what? 2. And I guess I am done with this. The correct option is A. And that's the solution to this Bernoulli's equation number 17 of our revision. We shall be moving on to another question, number 18. Question number 18. It reads, solve the IVP y prime equal to 6y squared x at y of 1 equal to 1 over 5. Alright, for this question, we are to solve the initial value problem. Look at the condition given to us, y of 1 equal to 1 over 5. The fact that the value of x and y here are not the same, this IVP, they could have used BVP, that is boundary value problem. Is that okay? And it's still the same procedure of handling the problem. Okay, now let us solve this question. The differential equation given to us, y prime, that is dy dx, right, is equal to 6y squared x. Now a clear look at this differential equation tells us that it's a separable variable ODE. Yes, we can separate the equation x to one side and y to one side. So this is what I'm going to do. I'll bring this y squared to this dy part and then take this dx part to the right hand side. Is that okay? In doing that, I'll have 1 all over y squared dy equal to 6x. It's just like I'm cross multiplying, but I want to separate so that the differential coefficient will be on different sides of the equation. X to the right, y to the what? Left. So the x going to the right, we are now going to get 6x dx. Good. This y square coming here is as a denominator. So we've separated the variable. All that is left for us now is to integrate. Integral 1 over y raised to the power 2. To handle that integration, you have to rewrite it as y raised to the power what? Minus 2. And so if you have y raised to the power minus 2 and you are to integrate, add 1 to the power, divide by the what? New power you get. If you add 1 to minus 2, you get plus 1. That is minus 2 plus 1, which is equal to minus 1 as power. In fact, resolving this, the integral will give you minus y raised to the power minus 1, which is the same as minus 1 all over y. Good. Now we're going to equate this to, we have integral 6x dx. That 6 is a constant, so pull it out of the integral sign. You have 6 integral x dx. If you integrate x, you are going to get x squared divided by 2. I've integrated this, so you put plus c, your constant of integration. Clearly, this and this will cancel, so you get 3 here. And so this is actually negative 1 over y equal to, we're going to have 3x squared plus c. You see, this is an IVP problem. So the solution we are looking for is not just general solution, but particular solution. One in which we are expected to get the value of this constant. That's why we're given that condition. When x is equal to 1, the value of y is 1 over 5. That is the meaning of y of 1 equal to 1 over 5. This is the value of x, which is 1. And this is the value of y, which is 1 over 5. So when x is 1, y is 1 over 5. We can substitute here and then get the value of the constant. Negative 1 all over, in place of y, you put 1 over 5. That's going to be equal to 3 times the value of x is 1. Then you raise it to the power 2 plus the constant of integration. Solving this will give you negative 5. Is that okay? Because this 5 will go up, division of fraction. Just basic arithmetic. Is that okay? And that's going to be equal to 3 plus c. What does that tell us? Therefore, the value of c is equal to minus 8. Remember that this 3 will come to this minus 5 to give us minus 5 minus 3. Now we've got the value of the constant of integration. We can now go back to our general solution. Substitute for that constant c. Every other thing will remain the same there. So we do that. It implies that the IVP solution will now be minus 1 over y equal to 3x squared. Then this plus c, because we have obtained the value is minus 8. That plus will change to minus. This is my solution. But looking at the option, you notice that the solution is not there directly in the option. The option tells us that y is made subject of the formula. So I'm going to quickly make y subject of the formula here. And to do that, I'll first of all multiply through by minus 1 so that this part will even be positive in the first place. That is simply 1 over y. If you do that, you get 1 divided by y equal to this negative. If it affects this will change to minus. If it affects this will change to plus. So this is actually 8 minus 3x squared. And then for y to be subject of the formula, it's just like cross multiplying, it goes to the right, and this term will come below as denominator. Therefore, y is equal to 1 all over 8 minus 3x squared. This is my solution. And of course, we know that y is always written as a function of x. And so I can simply still put y of x. I commit no crime, just like we have it in the option. This is my answer. Going back to the option, then we could see that the correct answer is option C. Good. Let us move on to question number 19. The 19th question reads, if x raised to the power of minus 1 dy minus x raised to the power of minus 2 y dx equals 0 is an exact equation, find the general solution at y equal to 2, x equal to 2. Once again, this is an initial value problem for which we are told that the given differential equation is exact. And so we have to obtain the solution of this at this given point. Is that okay? For exact equation, of course, it's a simple problem. When you're given an exact O.D.E. We have that x raised to the power minus 1, okay, minus x raised to the power of minus 2 times y dx is equal to 0. Since the problem said that this is an exact equation, we don't really need to check whether it is exact or not. As a matter of fact, an exact equation is the simplest form of first order ordinary differential equation to tackle. So we're going to solve this straight on by applying the first method of handling this. Yes, there are two ways you can solve an exact equation. Always from GMAS 41, we use a direct approach, of course, especially when we are dealing with past question. For detailed understanding and how to solve this in the other method of it, always remember you can contact the GMAS 41 to join us, okay, at a paid subscription, quite affordable. Is that okay? Check the comment section and you get further details about it. So we're moving on. We are going to integrate this directly. I'll simply write integral x minus 1 dy. I'll be integrating here with respect to y minus integral x raised to the power of minus 2 times y dx. I'll be integrating this part with respect to x. And then that will be equal to, if I like, I'll put integral 0 is my choice. If I don't like, I can remove the integral sign. Once I'm done integrating, I'll simply put equal to c. Besides, the general solution for an exact equation is given as a function that depends on x and y made equal to what? A constant. So we are trying to generate that function, that solution, are you getting me? Which will be equal to a constant for an exact equation. So simple and straightforward, given an exact equation with the terms, on one side, simply introduce your integral sign and integrate with respect to the differential coefficient we have there. We are integrating this with respect to what? Y. So that x raised to the power minus 1 would remain as a constant. It simply means that, remember, x raised to the power minus 1 is the same as 1 over x. Permit me to change it to that. 1 over x. And then we are integrating here with respect to y. So what is going to happen? Since 1 over x, or x raised to the power minus 1, is taken as a constant here, because the integral is with respect to what? Y. So it's just like you have the x raised to the power minus 1, or 1 over x as I wrote, then integral dy. And if you have integral dy, it simply welcomes back the variable you are integrating with respect to, which is y in this case. So this is going to be times y. Is that okay? Dot y. Good. And then we're done with this part. We're going to have negative. We come over to this and then integrate this part as well too. But this time around with respect to what? X. So what do? This y will be taken as a constant, so it's going to be written this way, because the differential coefficient here is x. You are integrating with respect to x. Anything that is not x here will be kept constant. So this y is taken as constant, so we're now having something like y times integral of x raised to the power of minus 2 dx. And if we integrate x raised to the power of minus 2, of course we've been doing that, add 1 to the power, and then divide by the what? Power. So this is going to give us something like x raised to the power of minus 1, then divided by minus 1. I'm done integrating this, so it's not going to be equal to c. In this approach that I'm using to solve this exact equation, what are you expected to do? Once you are done integrating this part, you are expected to pick everything in the answer. That's the integral value you got from here and from here. Combine all of them. But if you have any one which is repeated, and that usually is the case when you are solving exact equation, because isn't this method, are you following right? There is this particular one, this term that will appear here in this integral and will also appear here when you integrate this term. And that is what we could see here. This is y over x, as you're saying, because 1 times y will give you y. And then coming here, you know that this is the same as 1 over x times y. Are you following? In fact, let me use blue marker to show that this, as you are saying, is the same as 1 over x times y. That's what you have here. Is that okay? Then observe something. This minus will change this to minus. I think I should just bring this term out. This is y over x. That's what we have here. Minus minus changes this to positive as well too. And then x raised to the power minus 1 is the same as 1 over x. That 1 over x times this y will give you y over x. Then that's going to be equal to c. So this is what I'm talking about. Observe that the integral value you got here is y over x. The integral value you got here is y over x. So simply pick only one of them. Only one of them will make up the general solution of this. Will make up the answer of this exact equation. If there are other terms in this integral, and that's so we have to pick them. But those ones will not be the same as any one of these. Anyway, let's move on straight. Picking one of these, the solution is y over x equal to c. So I can now say at x equal to 2, comma y equal to 2. This means that we're going to have 2 over 2 equal to c, and then c is equal to what? 1. In conclusion, therefore, we can say that the general solution is go to this, or the particular solution actually, because once we are given this value of x and y, it is particular solution we are looking for, even though the question said we should find the general solution. This is the general solution, okay? Now, particular solution will come to this, substitute for our constant of integration there, which is 1. And of course, this is the answer to this problem. So that goes with option B. And this takes us to our last question, number 20. And now, it is time for us to solve our last question in this episode, Unit 2 past question review. Question number 20. And the question reads, solve, open bracket, x minus 1, close bracket, y prime, that is dy dx, plus y equal to x minus 1 in bracket raised to the power of 2 using integrating factor. This problem given to us, if you look at this differential equation, I can tell you clearly that it is a linear first order ordinary differential equation, because of course it goes with the standard from my observation here, dy dx plus p of xy equal to q of x. Right, that's the standard form of a linear first order ordinary differential equation. And of course, that's what I have here. This is a dy dx. I can remove this x minus 1 because in its standard form, the coefficient of this dy dx is meant to be 1. So let us do that. No wonder we are told to solve using integrating factor, because generally, linear first order ordinary differential equation is a type of ODE that we solve directly using integrating factor. I'll be solving this by standardizing the given equation directly. This is y prime is the same as dy dx. I'm dividing through by its coefficient x minus 1 so that the coefficient of this y prime will be 1. Is that okay? So coming to this plus y, I will divide it by x minus 1. So that's going to be plus. Dividing this y by x minus 1 is the same as 1 over x minus 1, then multiply by y. Equal to, come to this term, and then divide this part by x minus 1. It will simply reduce the power by 1. So we'll be left with x minus 1. Now we solve a linear first order differential equation quickly using the integrating factor, which is why we are told to solve this using integrating factor. And how do we get the integrating factor? Simply, the integrating factor is given as anyway, I guess I should write the formula for you first. To solve this, the general solution is y times integrating factor. Is that okay? Y times integrating factor equal to integral, then q of x times integrating factor. This part, bearing integral sign, will integrate with respect to x. So what is our integrating factor? That's the first thing we get. To obtain our integrating factor, we are simply going to take exponential integral p dx. This is the integrating factor when dealing with linear first order differential equation. And of course, this is equal to exponential integral. Our p is the coefficient of y, is that okay? Which is 1 over x minus 1. 1 over x minus 1. We shall integrate with respect to x. If you have integral 1 over x minus 1, the solution by use substitution is simply ln of the denominator, that is ln of x minus 1. That's equal to exponential ln x minus 1. When you have exponential to the power of ln, what happens? They cancel out. It is just like taking a square root of a term carrying square, or taking the square of a term carrying square roots. Clearly then, our integrating factor is equal to x minus 1. That is our integrating factor. Good. And once we are done with this, our problem is as good as solved. Come to the formula and then substitute. The solution is y times integrating factor, that is y times, our integrating factor is x minus 1, equal to integral q of x times integrating factor. Look at that. Our q of x is this x function, this part on the right hand side, in the standardized linear first order differential equation. And here it is clearly x minus 1. So it's going to be integral q of x, which is x minus 1. We are multiplying it by the integrating factor. And what is our integrating factor here? Our integrating factor is still x minus 1. So if I multiply this q of x by x minus 1, you know what's going to be, right? It's going to simply be x minus 1 raised to the power of 2. So let me just do that. Instead of multiplying x minus 1 times x minus 1. Our work now is simply to integrate this part, which is going to give us y, open bracket, x minus 1 equal to integral x minus 1 all raised to the power 2. Simply add 1 to the power and divide by the power. So we get this. Alright, x minus 1 raised to the power 3 over 3. I'm done integrating, so you put constant of integration. And of course, this is my solution to this linear first order differential equation. But we have to simplify further as much as possible and as the option may demand. If you look at the option, clearly y has been made subject of the formula in them. So I'm going to make y subject of the formula here, which means I will divide through by the coefficient of y, which is x minus 1. Doing that, the value of y will be equal to, come over here and divide this term by x minus 1. What is simply going to happen is reducing this power 3 by 1, so you get power 2 there. X minus 1 in bracket raised to power 2. Then we have over 3 there, then plus, come to this constant of integration, divide by this x minus 1. And this of course becomes my solution. This is the solution of this linear first order differential equation solved using integrating factor. If you look at this, the options we have here, the correct option is B. This is actually y equal to x minus 1 in bracket to the power of 2 all over 3 plus c all over x minus 1. It's been a wonderful episode, because we've come to the end of our episode U2 2 past question review. O.D.E, ordinary differential equation. I hope you learned a lot following us through this episode. Please, kindly subscribe to the GMATS 41's YouTube channel so that once I upload any new content and of course other series or episodes, you will be personally notified. Of course, to get that notification after subscribing, please remember to turn on the notification bell. Like I've always stated, that's not all. You can join our full range of learning classes. Is that okay? On Telegram, you can get a paid access to it at an affordable fee. I hope to see you in our next episode, U23. You have a wonderful time. And always remember to check back. You have other wonderful things to learn from this channel.